How do you know if an object is curved or flat? In general relativity, there's only one thing you need to tell you if an object is curved or not, and that is the Riemann curvature tensor. The Riemann curvature tensor is one tool that tells you everything about how curved an object is. That object could be a black hole, could be a star, could be a galaxy, could be a planet, whatever it is, the Riemann curvature tensor will tell you not only if that object is flat or not, but how curved that object is as a dependence on theta, phi, and r, the radial parameter. So in this video, I'm going to show you how to calculate the Riemann curvature tensor for the simplest object possible, a star. In other words, a sphere. So let's go ahead and get started. So let's start off with a simple question. If I have an object, if I have a surface, how do I tell if that surface is curved or not? What do I mean by curved? Well, let's say I have a box, okay? And I'm like an ant on the surface of this box. Without zooming out and looking at this box from a bigger perspective, a bird's eye perspective, how do I know that this box is flat if I'm just an ant on the box? In other words, if I'm, for example, a human on the surface of the earth, how do I know that the earth is really flat without zooming out, without sending a rocket into low Earth orbit and taking a picture? In other words, is there a way to measure the curvature of a surface by being on the surface itself? In other words, is there a way we can measure the intrinsic curvature of a surface? And the answer is yes. The answer comes from this quantity, which is the Riemann curvature tensor. The Riemann curvature tensor is this 4-index tensor, okay, given by R. So it has 4 indices, let's say alpha, beta, mu, nu. And the Riemann curvature tensor depends on a couple of things. First of all, it's made out of 4 terms, and you are by no means expected to memorize this. The idea is just to understand how the Riemann curvature tensor looks and its symmetry properties. So the Riemann curvature tensor is made out of 4 pieces, and let me explain each one of them. The first piece of the Riemann curvature tensor is this Christoffel symbol. But it's not just any Christoffel symbol, it's a derivative of a Christoffel symbol. So these first 2 terms are derivatives. These are derivatives of the Christoffel symbol. So beta, mu, nu. So derivatives of the Christoffel symbol give you the first 2 terms of the Riemann curvature tensor. The next 2 terms of the Riemann curvature tensor are simply products of the Christoffel symbol. So these are products of the Christoffel symbols. So these are, let's say, Christoffel A, Christoffel B. Okay, and so now you might ask yourself, first of all, why is the Riemann curvature tensor made out of derivatives of the Christoffel symbol? Why isn't the Christoffel symbol itself enough to tell us if a surface is curved or not? And furthermore, what is the Christoffel symbol? And what does the Riemann curvature tensor itself tell us? Okay, these are all good questions, and they will all be answered shortly. The first thing I'm going to answer is, what is the Christoffel symbol? The Christoffel symbol is a very useful tool in general relativity that connects your metric G mu straight to the Riemann curvature tensor. So the Christoffel symbol is really a bridge. It's a bridge maker that takes you from the metric that describes your surface to the quantity that describes the curvature of your surface. So the Christoffel symbol is given as follows. If I have a Christoffel symbol with the following indices, let's say alpha, beta, nu, then here's how I can write down the Christoffel symbol. So this is 1/2 G, and then there's no memorization involved here. You just exploit the symmetry properties of the Christoffel symbol. Recall that if this contravariant index is alpha, I must have a contravariant index of alpha here so that I get a contravariant index at the end. And then I need some kind of a dummy variable to sum over. Let's call that sigma. And now I'm going to multiply this by G of, now I'm going to take this sigma, okay, and I'm just going to place these indices here, beta, and then comma, nu. This comma represents a derivative with respect to the new variable. And then because the Christoffel symbol is symmetric under the lower 2 indices, this Christoffel of alpha beta nu is also equal to Christoffel of alpha nu beta. Okay? And so that means if I switch these two indices, I must retain the same Christoffel symbol. And so I add that with a plus sign. But the Christoffel symbol will have one last metric term that's minus g, and then I have beta nu, the same order as it is written on the left-hand side. Take the derivative of that with respect to alpha, your dummy variable. Oh, sorry, sigma, your dummy variable. So that's the idea. That's what the Christoffel symbol is. Equal to, it's just derivatives of the metric. Derivatives of the metric. Okay, okie dokie, this is great. Now you know what the Christoffel symbol is. You see how it's related to the metric. And in fact, we can write the entire Riemann curvature tensor in terms of the metric as well. Now, what the Riemann curvature tensor gives you is a full diagnostic for whether or not a surface is curved or not. So for example, let's say we have two surfaces. This marker is garbage. Garbo. So let's say we have two surfaces. I'm going to draw a curved surface. For example, this could be some kind of a paraboloid. So here's a curved surface. And I'm going to draw a flat surface. So here's a flat surface. Maybe this is a sheet of paper. Now, for the curved surface, the Riemann curvature tensor will tell us that that curved surface has a Riemann curvature tensor of 0. Oh, sorry. Whoa. Okay. Whoopsie daisies. For the curved surface, the Riemann curvature tensor is not going to be 0. That's the whole damn point. That the Riemann curvature tensor is a diagnostic for whether or not a surface is really flat. Whereas for a flat surface, the Riemann curvature tensor is 0. Now, you might say, well, now hang on a second, Rev. Where are you taking us with this? Because isn't it true that if you have a flat surface, then you have Cartesian coordinates or polar coordinates, then isn't your metric itself going to tell you if you have a curved surface? And the answer is no, right? Because even if you have, for example, spherical coordinates, your metric is not going to look like Cartesian coordinates. For Cartesian coordinates, we know how to easily write down the metric. Let's do it right now. In Minkowski space, wow, all of my markers today are just garbo. What is going on? So in Minkowski space, we know that the metric is ds squared is minus dt squared plus dx squared plus dy squared plus dz squared. Now, if I write that as a matrix, then I have G mean u is minus 1, 1, 1, 1. This is just a Minkowski metric, eta mean u. But you might say, okay, so isn't that itself a good diagnostic for whether or not a space surface is curved or flat? And the answer is no, because even if you go to, for example, polar coordinates, then you have that ds squared is minus dt squared plus dr squared plus r d theta squared, r squared d theta squared. And so now G mean u is minus 1, 1 r squared. And so that r squared is enough to fool you into thinking that, hey, this is a curved space, when in fact you're just using non-Cartesian coordinates to describe a flat space. So the metric by no means is a measure of the curvature of a spacetime. You need to go to second derivatives of the metric to tell you whether or not a spacetime is curved. And second derivatives of the metric are first derivatives of the Christoffel symbol, right? So that's where this comes in. You might say, why is the curvature of a surface hidden in the second derivatives of the metric? Why not the first derivatives of the metric? And that is a very deep question. The reason why, in essence, is the following. If you have a curved surface, then at any given point, let's pick a point on this curved surface. Let's call this point P. If I evaluate the derivative of the metric at that point, it's going to be 0. In other words, if I write down, wow, all of my markers today are just bad, and it's embarrassing, and it's shameful, and it's disgraceful. So if I evaluate the metric G mean u at the point P, then it's going to be 0. For the very same reason that if you have a curve and you zoom into that curve sufficiently enough, then that curve becomes simply a straight line. Okay? And so the idea is that when you zoom into a curved surface enough, then it becomes a flat, non-curvy plane. with a metric. Oh, by the way, this should be derivative of the metric. What am I writing? So the derivative of the metric at a given point is 0, regardless of the curvature of your surface. So really, the metric doesn't tell you whether or not a surface is curved, because the metric could be changed even if you use a different coordinate system. The metric it depends on your coordinate system. It doesn't depend on the curvature of your space-time. The derivative of the metric is also not enough, because at any given point the derivative of the metric is 0, right? Simply for the reason that if you zoom into a curved surface enough, it becomes a flat plane. That's why when we look at the Earth doesn't look round to us humans, right? Because the Earth is much bigger than humans on the scale of humans. Humans are simply 1 meter. The diameter of the Earth is 12,000 kilometers, right? So on our scale, the Earth looks flat. On the scale of a point, any given surface, whether curved or not, is going to look flat. And so derivatives of the metric are not going to tell you whether or not that surface is curved. It's in the second derivatives of the metric that curvature is hiding. And so you have to shoot the Christoffel symbol with a derivative, which will give you second derivatives of the metric. And so those second derivatives of the metric are really what's encoding the curvature of your surface. That's why the Riemann curvature tensor depends on the first derivative of the Christoffel symbol, which gives you second derivatives of the metric. Okay, that's the idea. So that's a basic picture of the Riemann curvature tensor. Now, by the way, nobody actually remembers the Riemann curvature tensor off the top of their heads. That's why I've written it down on the very top of this lecture video here, so we can use it. And so now what I'm going to do is calculate the Riemann curvature tensor in full for a sphere, okay, for describing a sphere. So let's see. So apparently, despite the fact that this school has a $6 billion budget endowment, they don't spend any money on erasers, because this eraser can barely erase the whiteboard. In any case, let's now try to describe a spherical surface by using the Riemann curvature tensor. Let's derive the Riemann curvature tensor for a sphere. So, oh God. So here is, these markers are just depressing. So here is a sphere, okay? And the first order of business is to write down the metric describing the sphere. Let us say that this is a unit sphere with radius 1. So we typically have ds squared is equal to, let's just say we write down, not in Minkowski space, just in Euclidean space. Let's write down the metric. So this is going to be what? Usually it's dr squared plus r squared d theta squared plus r squared sine squared theta. Now in this case, r is fixed, right? The radius of this damn sphere is not changing. So dr squared is 0. And in fact, r is fixed to be a unit sphere. So that means we have d theta squared plus sine squared theta d phi squared. So here's our metric, and it's very simple. It only depends on theta and phi. So this is actually very handy. And so our G mu is simply going to be a 2 by 2 matrix composed of 1 and sine squared theta. Now, if this don't look like a joke to you now, then I'm sorry for you. So this is d theta on the first column, d phi on the second column. Now our next order of business is to evaluate the Christoffel symbols for this metric. So let's see, how are we going to evaluate the Christoffel symbols? So we have to be very organized in the way we compute them. Let's start off with, actually in general, what does the general Christoffel symbol look like? Well, it's alpha, beta, mu, and now I'm going to write it fast because I already explained how to recall the form of the Christoffel symbols. Alpha, beta, okay? Oh, sorry, this is beta mu, so this should be beta mu comma sigma. Beta, the price of being too smart. Okay, so at this point, we have to evaluate the Christoffel symbol systematically. So that's what I'm going to do. There are two choices for alpha, right? Two choices. Those two choices are alpha can either be theta or it can be phi. So let's start off with alpha being theta. So this is our first case. Alpha is theta. Let's evaluate all the Christoffel symbols for that case. So we have Christoffel of theta, and then we have beta mu. So beta mu can be anything. So let's start off with something basic. Let's say theta theta, just to show you an example. So we have 1/2 g theta. Now, of course, if this is theta, right, if alpha is theta, sigma must be theta. The dummy variable must be theta because we have a diagonal metric. And so this term, g alpha sigma, won't survive for any other sigma other than alpha. So if this is theta, which it must be because that's what alpha is, then this dummy index is forced to be theta if we want non-zero terms, which is, I presume, what we want. So now we have g theta for our dummy variable, and then beta and mu you can just plug in because they're both theta in this case, right? So this is, remember, alpha here. Alpha is theta, beta is theta, mu is theta. So if everything is theta, what you'll get after plugging everything in, something that's almost comical, which is a bunch of g theta thetas. And so here, these two guys cancel out. And so we're left with g theta theta. Take the derivative of that with respect to theta. But g theta theta is a constant. It's just 1. So this is 0, right? And so you find that this Christoffel symbol is 0, okay? Now, this is just a trivial one, but now let's upgrade to something more interesting. Let's say we evaluate g theta theta phi. Okay, so now we'll have 1/2 g theta theta, and then we'll have g theta theta phi plus g theta phi theta minus g theta phi theta, theta phi theta. Now let's see if I lost my mind or if these two terms actually cancel out. So we have theta theta phi, okay, that looks good, theta phi theta, and then theta phi theta. Okay, good. So it does seem that these two terms do indeed cancel. Theta theta is a constant because it's just 1. Remember, this is the g theta theta term. This is the g phi term. So this is 0 as well. And of course, these two cancel. And so this gives you another 0, which is shocking because that's not what I expected, but okay. Great. So by the symmetry of the Christoffel symbols, this is also equal to theta phi theta because we can exchange the lower two indices without sacrificing any signs or whatnot. Now we take a look at the second case, which is that alpha, that upper contravariant index, is phi. So if alpha is phi, then let's see what we get. Hopefully we'll get some non-zero results this time. Let's try phi theta phi. So phi theta phi is 1/2 g phi phi, then g phi theta comma phi plus g phi phi comma theta minus g theta phi comma phi. Okay, so now at this point, let's evaluate this thing. First of all, we know that any non-diagonal elements are going to be 0. So this phi theta component is 0, theta phi component is 0. Now here, this is interesting. We're taking the derivative of the g phi phi element with respect to theta. Finally, this is going to give us something non-zero. So we'll have 1/2. This is the inverse metric, g phi phi. So that'll be 1 over sine squared theta. And then here we have the derivative of the phi phi component with respect to theta. So the derivative of sine squared theta with respect to theta, I'll write it over here, is 2 sine theta cosine theta. And so we have 1/2 and 2 cancel out. Sine theta cancels out with one factor of that. And so we're left with cotangent of theta. So this is cotangent of theta. So great. So we've found, thank God, thank the Lord, that we found at least one non-zero Christoffel symbol. And so is there anything else that we need to consider? I feel like I made a mistake here. Theta theta phi, this is theta theta. This is theta theta phi. Okay, this is theta phi theta. That makes sense. And this is theta phi comma theta. Okay, it looks good. It's just, there should be at least one non-zero element for the thetas. But okay, that's the way it chooses to be, then I can't stop it. So then the last thing we'd like to see is, what about the Christoffel symbol where you only have phi's? Well, for the same reason that it was 0 for only thetas, it's going to be 0 here, because for the phi phi component, if you look at the phi component, there's no dependence on phi here. At the end, you're going to get 0. By symmetry, this is also equal to the Christoffel symbol for phi theta. So here's that symmetry relationship right there. So now we've got all the Christoffel symbols. Now we can plug them into the Riemann curvature tensor. At this point of the video, I'm actually too sleepy. I'll do that next time. So that's it for today's lecture. You've seen how to calculate the Christoffel symbols for a 2D for a 3D sphere, and you've seen why the Riemann curvature tensor requires the second derivative of the metric. Thank you for watching. I'll see you tomorrow.